Oh, man. Alright, I'm kind of winging this. It's like I do with everything else. I've been kind of thinking about how I want to go about this in my head for the past, like, day or two. I'll do my best, kind of make this all coherent. So I wanted to do a series of videos on quantum physics. Since the other day when I mentioned quantum entanglement in that other video, I really wanted to kind of explain and share some quantum physics stuff with everyone, because this is really fascinating stuff. It's interesting, and it's weird. Quantum physics subverts your intuition. You kind of have this sense, and it came as a shock to the scientific community when they first made all these discoveries, because you kind of have this sense that that you have an idea of basically how everything works in the world around us. And you'd think that when you go down on the smaller, like, subatomic level, that it would work basically the same, but just a lot smaller. And it really, really doesn't. It's weird, and it's really cool and fascinating. And some of it's a little creepy, and that's cool too. Especially, like I was saying, quantum entanglement, for example, Einstein called it spooky action at a distance, because it shouldn't be possible. But we'll get to that later. Right now, I thought this would be a really good way to start off on the subject. I want to show you a quantum physics experiment that you can do yourself. It's really easy to do. You can pick up all the supplies you'll need for like $5. I'm by no means the first person to do this experiment. You can search on, like, YouTube, and I'm sure you'll find like a dozen videos of people doing it. Probably. But, you know, this being that I share these videos with you guys, with all my friends, and I'll explain this. I can explain what's going on in terms that you should all be able to understand. So, this experiment is going to demonstrate Heisenberg's uncertainty principle. I don't know how well you can see this. I'm not sure how good the resolution turns up on the camera there. That's kind of an older camera. Not very old. It's still, you know, it takes an SD card, so. But here, I wrote that up on the board here, Heisenberg's uncertainty principle experiment. First, before we get to the experiment itself, I'm going to explain what we're doing. And let me explain to you, clarify what we mean when we talk about uncertainty. I mean, I'm sure you have a general idea of what that word means, but to really drive the point home, let's say I gave you a ruler and a pen or a pencil or a marker or anything, and said, here, I want you to draw a line that's exactly 1 inch long. Okay, and you took it, and I really don't need to be, you know, demonstrating this, but I think it'll help a little bit. And you draw a line, and ruler being the one thing I don't have on me at the moment. Got all this other stuff to do this experiment. Ruler? Nah. Not important, though. You take the ruler, and you're really careful, and you measure a line, and you get it right out to 1 inch mark. Let's just assume that's an inch long according to, you've got your ruler, you draw a line, it's 1 inch long, and you're really careful about it. And you say, okay, I drew a line that's exactly 1 inch long. And for all practical applications, it's okay to say that it's exactly 1 inch long, because anything that you might need, that you might need to do with that measurement, in any practical application, it's close enough. But understand that technically, you can never know that it's exactly 1 inch long. You could say, it's about an inch, but how do you know it's not like 1.00001 inches long? How do you know it's not 0.99999 inches long? You can't know exactly. You can only know depending on the preciseness of the instrument you were using. So say the ruler is marked off like eighths of an inch. You might know to within an eighth of an inch. You could say that, and we'll call this line, we'll use the variable L for length, and we're saying that L equals 1 inch. Again, I hope this is turning up on the video, it's clear, but if not, I'm telling you what I'm writing down. L equals 1 inch. But you don't know. Let's say you know that that's an inch. You know that to within an eighth of an inch, which is 0.125. So if you only know with a certainty of 0.125, then L could be anywhere between 0.875 inches and 1.125 inches. You're saying it's an inch. I know that to a certainty of within an eighth of an inch, 0.125 inches. So the way we're going to denote uncertainty with the Greek letter delta, we're saying L is 1 inch, delta L is 0.125 inches. That means, again, it's an inch. We know that to within 0.125 inches. It might be 1.125, it might be 0.875, or anywhere in between. And realistically, like, you might know it to within 1/100th of an inch. If delta L is 0.01 inches, then what you're saying is that the length of that line could be anywhere between 0.99 inches and 1.01 inches. So that's what that means. That's what we're denoting with the Greek letter delta. That's uncertainty. So, knowing that, my eye itches today. Knowing that, you already know half of the equation of Heisenberg's uncertainty principle. Heisenberg's uncertainty principle is delta x times delta p is greater than or equal to h bar over 2. X is position. I know you're probably thinking, why isn't P position? There's a whole, I don't know what else. Well, we can't use P for we can't use M for momentum. M is mass. There are reasons behind all these variables, but P is momentum. X is position. P is momentum. I'll get to the second half of this equation in a minute. Basically, layman's terms, position is where you are. Momentum is a product of your velocity and mass. Momentum is basically where are you going and how determined are you to get there, more or less, if you want to put this in simple terms. As I always say, accuracy is the first casualty of simplicity, but we're not really sacrificing a whole lot in terms of that, in terms of accuracy. Momentum is a product of your velocity and mass. Makes sense. The faster something's moving and the heavier it is, the harder it is to stop. That's basically what your momentum is. We're going to be talking in this experiment about photons, which are particles, well, not particles, gotta be careful, waves and particles, depending, little bundles of light. Packets, let's call them that. They're like packets of light, which are massless, no mass. They kind of have like an effective mass for, it's kind of hard to explain. But at any rate, we're going to assume their mass to be fixed for this experiment. So, and light travels at a constant speed. So, when we talk about momentum in this experiment, we're going to be talking about what direction is it moving in. Okay? So position, momentum. Position is where is it? Momentum is what direction is it moving in. Our uncertainty regarding its position and our uncertainty regarding its momentum, the product of those has to be greater than or equal to, meaning at least, this. H bar is the reduced Planck's constant. It's something like 1.05 times 10 to the, I believe it's negative 34th, and the units are something like joules seconds, joules times seconds divided by radians. It's, you don't really need to understand all of that. All you really need to know for this is that this number is incredibly small. It's almost inconceivably small. We're talking on the scale of like individual subatomic particles. And it's a good thing, because as this equation, what this is expressing, if this number were large, everyday objects wouldn't have like a definite position and momentum. The fact that this is small is the reason I could take like this marker and set it down on a surface, and I can know, we can say, where is the marker? Right there. And how fast is it moving? It isn't. It's stationary, and we know right where it is. And you can know that with a great deal of certainty, and this applies to everything. You can't know it to absolute certainty. Excuse me. You can't know it to absolute certainty, and it's not a that's not a consequence of our limitations, the limitations of our perception. This is inherent in reality, again, like I said, this number is very small. If I stand here and I'm standing still and my position changes by like the diameter of an atom, you're not going to notice. And that's why on this scale, this really doesn't apply. But when you get down to something as small as subatomic particles and light, this matters. So let me rewrite this. H bar over 2. We're saying that between these two properties, and there are several pairs of properties like this, but these are by far the most well known, and these are the two we're going to be working with in this experiment. Between these two properties, we must always be at least this uncertain. Basically what this means, between where it is and what direction it's going in, between those two, there needs to be at least this much uncertainty. Think about where I wanted to go next with this. So what we're going to be doing is we're going to take, I may as well explain everything we're going to need for this experiment. Again, like I said, you can perform this experiment at home, and I encourage you to. It's cool. Very basic stuff. It's the equipment for it, if you can even call it equipment, is going to cost you like $5. You can run out to like Walmart and pick up everything you're going to need for about $5. We're going to be using Play-Doh. Just a little bit of Play-Doh is fine. 2 razor blades. And a laser pointer. And I've got a clothespin here just to keep the button on the laser pointer held down for when I need to. Funny story behind picking this stuff up. The day that I decided I wanted to do this, I didn't even realize at the moment. I mean, I knew, but I didn't, it wasn't like a present issue on my mind at the moment. I'd totally forgotten. It was Christmas Eve when I went to pick this stuff up. And just to think of what kind of image it must have presented. A guy standing in line at in Walmart on Christmas Eve holding a little tiny tub of Play-Doh, pack of razor blades, and a laser pointer. I can just imagine what that must have looked like. Some child out there is about to have a very sad Christmas. Now, what we're going to do is I've got the 2 razor blades next to each other with a small gap in the middle in the Play-Doh. We're going to set it on a surface like this. As a matter of fact, here, I'm going to point this, there we go. You see that? I'm going to set this right here Can we see that on here? I'm sorry, I'm coming back here to make sure. Okay, good. And you can see we've got a little opening in here. And what I'm going to do is shine the laser pointer right between those two. That's good. Right there should work fine. I'm shining the laser pointer in between the razor blades and projecting it onto the whiteboard, which you can see there. Good. I hope this all comes out okay on the camera. Okay. You can see I've got the laser pointer shining between the two gaps in the razor blades. Right now, let's say those are positioned just like this. These are the two edges on the razor blades. And what we've got, laser pointer pointed right through those, and there's a steady stream of photons coming out of the laser pointer through the razor blades and striking the whiteboard. And because the gap between those is sufficiently wide, as photons go through there, we don't know their exact position with a whole lot of certainty. They could be here, they could be here, they could be anywhere in between the two razor blades. Because we don't know with too much certainty what their position is as they're passing through, their momentum can remain certain. They're going straight forward. And so we get a nice concentrated little dot here. Because those are passing through a wide enough gap. We're not certain of their position. We can be certain of their momentum. They're going straight forward. What I'm going to do is move these razor blades closer together. And eventually what's going to happen is we're going to reach a point where the gap between them is so narrow that we have defined the position of photons passing through it with too much precision. We know their position too precisely. That it's basically going to put us in danger of violating this. But we can't violate it. That's impossible. So what's going to happen is, and we're talking specifically about their position and momentum along this axis, left and right of the gap between the razor blades. What's going to happen is that as they pass through that tiny hole in between the blades, their position is known too precisely along this axis, and therefore their momentum along that axis is going to become erratic. And at that point, when you reach there, they go, oh shit, our position is known too well. And they're not saying this, obviously, I hope you know that. Our momentum needs to become less well defined, and so they aren't going to go straight forward anymore. Some of them are, because that's one of many possible trajectories, but others are going to start veering off to the left and to the right and in all directions, and the more narrow we make that gap, the more erratic the momentum is going to become. And so what you're going to see is this concentrated dot is going to spread out and narrow into a line, because what we've got, instead of photons coming straight forward, we've got them going straight forward until they hit that gap. Again, their position is too well defined, and they're going to start veering off to the left and to the right, and we're going to get a line. So keep your eye. Am I in front of this? I don't want to stand like right in front of the camera. I hope, and this might take me a minute to properly adjust these. So we're going to close this hole. Come on. Need to center this a little better. Narrow that gap. Sorry about this. Should really have it's not coming through at all. Good thing I can edit this. There we go. There. See it? Hold on. This worked a lot more easily when I wasn't trying to record it. There, we see that line? I don't know if it's showing up as well on the camera as I hoped. Well, I don't know how well it's showing up on the screen, but if you can take my word for it, that dot, let's try it this way, as I open and close these, now it's a dot, now it's more of a line. Like I said, you can do this at home, and that might be the better option. See if we've got that. Okay, yeah, it's probably not showing up really well on the camera, and I apologize for that. Try to zoom in on this. Yeah, unfortunately I think it's a little bit too faint. You're still we're looking at the middle of it. Tell you what I will do, I'm going to try it this way. I will try to snap a picture with my phone, and I'll kind of insert that into the video. Because it's still mostly concentrated in the middle. But when I put this on the video, I don't know, is this going to show up all enough? Like a screen on screen here. You can kind of see how it's radiating out. There's a line radiating out from the brighter spot in the center. And that's happening because the position of photons as they're passing through that hole is too well defined. And so their momentum is no longer definite. There's the momentum has to compensate for the certainty in position by becoming less certain. That's pretty much, I think that's all I wanted to cover with this experiment. This is really, this is the first lesson. I'm not sure, I may do more. It kind of depends on, if anybody's interested. So, take care everyone. See you next time.